Hello everyone. In this lecture, we will talk about shear stress in thin walled beams. Today, our objectives include introduce the thin walled beams and calculate the shear stress in thin walled beams. So previously in the last lecture, we analyzed two cases. It's in where we analyzed the beam segment like this. So in this way, we assume that we can say that the flange and the web are both thick. So what are thin walled beams? Again, if you have a cross section with the flanges and the web, if their aspect ratios, for example, like this, if their aspect ratios are very large, then we can call them thin walled beams, right? Like this. Okay, those are the thin walled beams. So today we will just introduce the concept of shear flow, and then we analyze the shear stresses in thin walled beams. Okay, this is our section 7.3. So let's start from the previous cases. Right, in the last lecture, we introduced two cases. We analyzed a beam segment as shown here. So we added a negative bending moment to it, and then we analyzed a case 1. This is our case 1 and a case 2. Right. So in both cases, let's look at the case 1. Okay, we have analyzed that if you add a negative bending moment to it, so if you look at one of the flanges, the resultant forces Fr and Fl will be different. Right? Fr will be Fr pointing right and Fl pointing left. Okay, in these two forces, Fr is larger than Fl, since they are tensile forces, right? So the combined effect of these two forces will be pointing right. So the delta F will be pointing right. So as a result, you need a shear force to balance it, to make sure this flange is in equilibrium. So this shear force V will be on this interface, right? On the interface between the yellow colored flange and the gray colored web. Okay, so this is direction of the V. And in the case 2, we analyzed the interface between the cap and the web. Okay, you can do the same analysis. Later you will find that the resultant force here, Fr, is larger than Fl. So the delta F will be pointing right. So to balance it, the shear force generated on this interface will be pointing left. Okay, so those are the two shear forces generated at the interfaces or virtual interfaces to balance the resultant forces due to bending. Okay, let's look at this beam segment and the two cases again. As we just analyzed, the shear force here is pointing left, and the shear force here is pointing left. Okay, and let's draw the preface, the intersection, a preface of this beam segment. Okay, it's a bit like this. Okay, this is the preface of this beam segment, and our interface 1 in case 1 is here. Okay, let's call this interface 1, and our interface 2 is here. Okay, this is interface 2. Okay, and we also analyzed other cases. Right, we can have a interface 3 here, and we can have a interface 4 here, right? So you can analyze the interface 3 and interface 4 in very similar ways, basically the same ways as in our case 1 and case 2, to derive the directions and values of the V on the virtual interfaces, right? So let's compare these values, the magnitudes of the shear stress, or shear force, or shear stress on these interfaces. So first of all, let's compare tau 3. Let's compare tau 3 and tau 1. So we need a sign here. So which one is bigger? Which one magnitude is larger? Tau 1 or tau 2? Tau 1 or tau 3? Okay. To answer this question, we need to do analysis. Right. Just keep in mind that our tau equals VQ over IT. Right. This is the equation we derived the last time. And in this equation, V is constant, right? I is a constant. Just at a point, a random point, the V is a constant. The shear force, overall shear force, is a constant, and the I is also a constant, right? The Q and T are variables, right? So here, let's compare the Q1 and the Q3. Q1 and Q3, which one is larger? Okay. Here, obviously, if you do this analysis with the Q equals AD, right? Q equals AD, and obviously the A1, A3, which one is larger? Okay, look at here. This is A1, right? And this is A3. So obviously A1 is larger than A3. So how about D1 and D3? This is the centroid of area 1, and this is the centroid of area 3. Okay, assume that here is the global centroid, so their D values should be the same. Okay, so D1 equals D3. Since Q equals AD, so Q1 should be larger than Q3, right? Then how about T? T1 and T3. T1 and T3, which one is larger? Okay, T1 and T3 should be equal to each other, right? Since here is the T1, here is T1, and here is T3, so T1 equals T3, right? So if you have a Q1 larger than Q3 and T1 equals T3 according to this equation, you can easily derive that the tau 1 is larger than tau 3, right? Then let's analyze the tau 2 and tau 4. Okay, tau 4 and tau 2. Which one is larger? Okay, we can do similar analysis. This Q4 and Q2, which one is bigger? Q2 and Q4, which one is bigger? So here, again, we can also analyze this from A4, A2, and D4, D2. Okay, and here is A2, and here is A4. So obviously A2 is larger than A4. A2 is larger than A4, right? So how about D2 and D4? Since the 4 is local centroid of 2 is here, 4 is here. So obviously D4 is larger, right? So D4 is larger than D2. Then if Q equals AD, which one is larger? It's hard to answer, right? It's not that easy to answer, but I can tell you that Q2 is larger than Q4. Okay, you can verify that based on simple calculations. Then how about T values? T2 and T4, which one is larger? Okay, T2 is smaller, right? T4 is larger here. Since here is T2, right, from here to here, and T4, this is T4. Okay, so T4 is larger than T2. In here you will have a trouble. So if you have a Q2 larger than Q4 and the Q2 is larger than Q4, and T2 is smaller than T4. So in this equation, how do you compare these tau values? So tau 2 will be larger or smaller? Tau 2 will be larger actually. Okay. Then we can verify this through a stress analysis. So based on this drawing here, so you can do analysis. If we want to analyze the distribution of the red colored stresses, okay, the tau value on this red colored interfaces, we can have a lot of interfaces as shown here. It have T1, T3, and other T values. If you want to analyze them layer by layer, so you will see that at the left end, the value will be 0, right? The value will be 0. Since at this interface, the value will be 0. Since A equals 0, right? A equals 0, that's Q equals 0. So the tau equals 0 at the left end. And on the right end is also 0. So they keep increasing, following the distance from the ends. So we increase then since the T1 will be larger than T3. So here you get a maximum value. Here you got a maximum value at this right hand side of this web. So if your web is thin enough, if it's not thin, you need more analysis, right? If the web is thin enough, you can approximate it into such a case. Okay, so the tau distribution will be like this. It's 0 at the ends, and in the middle, it may approach a largest value. So how about here? How about distribution in this direction? And obviously, at this end, it will also be 0, right? But following the distance from this face, here is the global centroid, right? So from following the increase of distance from the top, then the value will keep increasing. As we mentioned that tau 4 is smaller, right? Tau 4 is smaller than tau 2, so it keep increasing to 0.2, to the interface 2. So what will happen after this? What will happen after this? Okay, you can see that when it's crossing this interface 2, the Q will keep increasing, right? But the T will become smaller significantly, right? From a larger value to a smaller value significantly. It's a jumping. So as a result, the tau value will be jumping. Right? Then before it's reaching the global centroid, it will keep increasing slightly. Then after that, after reaching the global maximum, it will be decreasing to 0. Okay, so here is the global maximum. Okay, so this is the distribution. So you can see that the stress, the shear stress, tau 2, here is the maximum value of tau 2, right? This tau 2 can be much larger than tau 4. Actually, here is a tau 4, right? Then it is in the previous case, we just compared tau 1 and tau 3, then tau 4 and tau 2. Then how about if I let you to compare the tau 1, tau 2, tau 3, and tau 4? So can you do this analysis? So here we need to do further analysis. Okay, here it's not covered in case 1 and case 2. Here is a new case. Okay. So here let's draw this preface here. We draw the preface here. And so we have this preface. And our this is a 1 and 2, right? And we also have a 3 and a 4, right? So then we will just cut a random element, since those positions of 3 and 4 are random, right? So we just cut a random element from here. Okay, we cut a 3-dimensional random element from here. Then we can take this out. Okay, take this out. Then we will draw this 3-dimensional stress element. This is the preface. Then you will have a interface. The red colored thing is the interface we analyzed in case 1. Okay, this is the interface in case 1. And then we have another interface. Another face here. This is the face, the interface we analyzed in case 2. Okay, we already concluded that on these two interfaces, our resultant, the generated shear force is pointing left and pointing left. Right. So on here, on these two faces, so these two forces will be, two stresses will be like this. Okay, so according to the general distribution, general symmetry of these shear stresses, as as introduced here in this frame. So here is a theory, basic theory of the symmetry of the shear stresses. Okay, according to the shear stresses, these two components, the red colored and green colored components, will have their symmetric components on the preface. So you will have a transverse component. Let's see, it's a transverse component, tau trans, and a vertical component, tau v. Okay, so the tau transverse equals tau 3 here, since this is a random phase of random interface 3. Okay, let's call it tau 3. And here is a tau 4. Okay, so this is a randomly cut three-dimensional stress element. Okay, then the tau transverse can be tau 1 or tau 3 or others, depending on position. Right, depending on where you cut this element. And the vertical components can be tau 2, tau 4, or others, depending on position too. Okay, so here, since in case 1, case 2, we used tau 3 as a random case, and we used tau 4 as a random case. So we just say tau transverse equals tau 3 and tau vertical equals tau 4. Okay, so then it will become a comparison between tau 3 and tau 4, right, or tau 1 and tau 2. Since previously we compared tau 1 and tau 3, and you have concluded that tau 1 is larger than tau 3, and you compared tau 2 and tau 4, and you concluded that tau 2 is larger than tau 4. Then how about you compare them? You compare tau 1 and tau 2, tau 3 and tau 4. So which one is larger? So here we will just do this comparison. Then this will be important. It's at a random element, you can see that on the preface you have both components, tau transverse and tau vertical. So which one is larger? Which one is smaller? And is that possible one of them will be much larger than another one, so you can ignore the smaller one, only consider the dominant shear force, shear stress. So this is the purpose of this comparison. Okay. So here just at a random point on the flange, we cut this random element. So let's do this comparison at a random point. And we have a tau transverse and a tau vertical. So, which one is larger? Which one is smaller? Can we do this comparison? Based on the previous analysis, to do this comparison, since tau equals VQ over IT, and V and I are constant, and Q and T can be variables. So it depends on. So this comparison will depend on position, right? Will depend on position. Depend on the Q values and the T values, or the ratios between Q3 and Q4, and the ratios between T3 and T4. Okay, it's Q3 over Q4 and T3 over T4. So which one is larger? Which one is smaller? Based on these comparisons, you can compare the two values, right? So it will be complicated comparison in the previous case 1 or case 2, case 1, case 2, since those flange, cap, webs, they are all thick, right? Their dimensions will be comparable to each other, and their aspect ratios are small. So in this chapter, in this section, we're studying thin walled structure. So let's compare these two stress values in a thin walled flange, in a thin flange. So here is just the question: how about if the flange is thin? That means if in the flange is like this, okay, it's very, very thin. If it's very thin and the randomly cut element is here, right, then again the tau equals VQ over IT. Then let's compare the tau transverse and tau vertical again. Okay. So here the Q will be less affected, but the T will be very different. So which one is bigger? So if you compare T3 and T4, okay, T3 and T4, which one will be bigger? Okay, recall this analysis in case 1 and case 2. Where is the T3? Where is T3? Here is the interface 3. Here's interface 4. Okay. So you can see that here will be our T3, and here will be our T4. Okay. So you can easily do this comparison. The T3 is much smaller than T4. So since the T is below the line, your T transverse will be much larger than the T vertical. Okay, so we can conclude that on a thin flange, the transverse tau dominates. Tau transverse, or a horizontal, the horizontal shear stress dominates. And the vertical components of the vertical shear stress will be much smaller, so you can ignore it. You can do a similar analysis. and derive that on the thin web, shown here. Right, this is our web, right? If this web is thin, meaning that if you have a web like this, very thin, okay, you can derive that on a thin web, the tau vertical dominate. Okay, you can get these two important conclusions. Okay, here is our conclusion 1 and conclusion 2. Okay, based on these two conclusions, so what are the shear? What is the shear distribution on the preface of this thin-walled T-shaped beam? Okay, you can see here. This is our thin-walled This is the seaward beam. You can see that since on the flange you have a you have the transverse shear stress dominates. So this will be like this. The transverse shear. This is on the left hand side we analyzed. Since we derived here the direction of the transverse shear stress is pointing left on the preface, so we got this flow. And you can do another analysis on the right hand side of this flange, the right flange. The shear will be pointing the other direction. And on the web, the vertical shear will dominate. So this is the shear flow on the thin web. Okay, you can see these flows. Why this flows, the green colored and the red colored flows of the shear. So that is why we call it as shear flow. Okay, this is the concept of shear flow. We're not saying that on the flange you do not have the vertical shear. You have it, but the value is very, very small. It's much smaller than the transverse component, than the transverse shear stress. So we ignore the small value. We only consider the dominant shear. So we got a flow. Okay, actually, on both flange and web, you have the shear on two directions, but one of them is much smaller, so we ignored it. We only consider the dominant shear stress, so we got this flow. Okay, so this is on the seaward beam section subjected to a negative bending moment. And sometimes, of course, your seaward beam will be subjected to a positive bending moment. So what will happen in such a case? Okay, here this slide is summarized such a case. You have an I-shaped seaward beam section, then you're subjected to positive bending moment as shown here. Okay, those are the positive bending moment. You can repeat the analysis in case 1, case 2, and the new case. Then if you focus on this part, right? Focus on this part, and as shown here, you just focus on that part. You cut it off, and you got an element, got a three-dimensional stress element here. And so you can easily, according to the cases, the case 1, you can easily derive that when this beam segment is subjected to positive bending moment on the top flange, it will be subjected to compressive stress. So on this segment, the combined effect of the force will be a delta F pointing left. So on the interface, the shear force will be pointing right to balance this delta F, right? So on this element, you will have a shear stress pointing the right hand side. So you can draw this stress element here as we did in the previous slide. I draw this element here, but this element was cut on the right hand side, not the left hand side, so it will be a little bit different, right? So you will have the face here and the face here. Okay, it's as we just derived here, right? The direction of the shear on this interface will be pointing to the right hand side. So on the preface, is pointing outward, right? So on the bottom, you will have a shear stress pointing outward too. Okay, So according to the symmetry of the shear stresses, on the preface you will have these components, the tau vertical and the tau transverse. Right. So you can do the same analysis as the previous slides. Then you will see that on the flange, the tau transverse will be dominating, and on the web, the vertical stress will be dominating. So as a result, the shear on the web will be on the flange will be like this. Okay, this is on the right hand side. On the left hand side, it will be flowing in this way, and on the web, the vertical stress will be dominating, pointing down. Then on the lower part, it will be the same as the flange subjected to negative moment in the previous slide, right? It will be pointing right on the right hand side and pointing left on the left hand side. So you can see a complete flow. Okay, this is a complete shear flow. Okay, it's flowing in such a direction. Right? So this is shear flow when this segment is subjected to positive moment. Okay, you can compare it with the previous case. You can see that in this case it's flowing from the bottom to top, and when subjected to positive, it's flowing from the top to the bottom. Okay. So in the seam-walled beam, then we will have another concept apart from the shear stress. Since the shear stress equation will be a general equation, you can use it everywhere. The tau equals VQ over IT. Right? We can define another thing called shear flow. This is the Q. Shear flow equals tau times T, or VQ over I. Okay. This is another concept called the shear flow. So you can compare these two concepts. Since the V and I are constant in the section, no matter where this point is locating, at that point, both V and I are constant. Right? The Q and T are variables and depend on the position where you are analyzing the stress. The Q is maximum at the centroid. Right? Q is always maximum at the centroid. Since if you have a centroid here, right, the Q equals AD, right? So when you're analyzing here on the top, A is 0. So when you're moving down, A is increasing, and D is also changing. But as a result, the Q will be increasing all the time until it reaches the global centroid. Okay, the Q is just increasing from the top towards the centroid, and can also increase from the bottom towards the centroid. So you get the maximum Q at the centroid. This is always valid. But the stress is not necessarily maximum at the centroid for a seam-walled structure, because it also depends on the thickness at the position you are analyzing. Okay, in such a case, you will see that if you have a seam-walled flange, but a very, very thick web, so what will happen? If you're comparing two cases, one case is here, and one case is here. Okay. The Q is 1 and 2. So Q1 and Q2 and the T1 and T2 here. Okay. The Q1 will be smaller than Q2. but T1 is much larger than the Q2 is much smaller. So sorry. Okay, yeah, so here is the case. Okay, it depends on the position where you have different t values. This is sometimes you have a very large Q, but you can also have a very large t. Okay, very large t. We're not analyzing this case. We're analyzing such a case here. Okay, if you have this t and this t here. Okay. So when you have a larger Q, but much larger T, though you're not necessarily get a larger tau value, even though you have a larger Q. Okay, so this is the case. So if you're analyzing the shear flow, it doesn't depend on T. It is equals VQ over I. So it only depends on Q. In this case, if you have a larger Q, you will have a larger shear flow. Okay, so we can say that the shear flow, lowercase q, it's always maximum at the centroid of section. Okay, so at the centroid of section, the global centroid of the section, you will get the maximum Q and maximum shear flow, but not necessarily the maximum shear stress. Okay.